is the lecture for section 5.1 part B. So let's go ahead and get started. Let me start by sharing my screen here. Alright, there we go. And there we go. Alrighty. So let's get started. If you recall, on Monday, when we started with section 5.1 part A, we left off by having a conversation about divisibility. And we talked about how, we had started that section by talking about factors, figuring out what created factors. We talked about prime factorization and how to find it. And we left off by discussing divisibility, i.e. that factors of a composite number, if you recall we gave definitions for what a prime number is and what a composite number is, factors of a composite number will have to be either made up of, we discussed how there were two ways that we could find them. They could either be found by finding the two numbers that multiply together give you the composite number in question as the product, and then we discussed how divisibility can also be found by finding a number. In the case of our conversation, we were talking prime numbers, but finding a number that divides into the composite number in question evenly, i.e. with a remainder of 0. And if that is the case, then that number that we are dividing into the composite number is a factor of that composite number, along with its corresponding quotient. So that's what we're going to talk about today, because there are some tests that we can use to determine what factors are divisible into a particular number that we are discussing. This is a good way to be able to determine the prime factorization of a number, because if you can check divisibility, you know what prime factors to choose from when creating your factor trees. It's also useful when doing long division, so when you're teaching that concept, understanding divisibility helps the concept of division to be taught more easily, along with the concept of fact families between multiplication and division. So there are a lot of useful applications to understanding the divisibility of any given particular composite number. So we're going to talk about some tests for divisibility, all right? And we're starting right here. Now, what is the test of divisibility? A test for divisibility is defined as, simple tests that can be used to help determine the factors of a particular number. Think composite number here. Although we can talk about prime numbers, but just as in their definition, a prime number is defined as a number that has only two factors, one in itself. If you're talking divisibility, it will only be divisible by one in itself as well. So we're going to expand our conversation to really focus on composite numbers. Now, we group tests for divisibility together into groups, and we're going to start by looking at the divisibility by 2, 5, and 10. Okay, this is called Theorem 5.2, as you can see right here. Okay, and Theorem 5.2 states the following: that a number will be divisible by 2 if and only if the ones digit is 0, 2, 4, 6, or 8. Basically what this means is any number whose ones digit is even, i.e. therefore the number being even, will be divisible by 2. Okay? Now, a number will be divisible by 5 if and only if the ones digit is 0 or 5. So basically any number we're looking at, if it ends with a 0 or a 5, then you know it will be divisible by 5. And last but not least, a number will be divisible by 10 only if the ones digit is 0. So that you can see why they're grouped together, because if a number has a ones digit that is 0, then it will be divisible by 2, because you can see that 2 is one of the numbers that could be in the ones place to determine that a number is divisible by 2 if there's a 0 there. It will be divisible by 5 if there's a 0 there in the ones place of that number, and it will be divisible by 10. So that's why they're grouped together, because if any given composite number that we're looking at has 0 in the ones digit, then right off the bat you know it is divisible by 2, it is divisible by 5, and it's divisible by 10. Okay? And then of course you see the other things that apply for 2. Basically any even number is going to be divisible by 2, and any number that also ends in a 5 will be divisible by 5. Okay? So the way that is theorem 5.2, and it tells you about the divisibility of 2, 5, and 10, meaning a number that will be divisible by 2, 5, and 10 evenly, having a remainder of 0. Okay? Now, let's look at theorem 5.3. Okay? Theorem 5.3 states that if we let a, m, n, and k be whole numbers, so we're letting these variables represent whole numbers, and we also say that a is not going to be equal to 0, okay, then, and here's the notation we use, it is important to note that notation. This little letter before, in set theory, it stood for such that. Now, in this conversation, it refers to divides by, okay? So it's important to note that. And I'm going to highlight it so as to not block our conversation. So it is important to note that that little line means divides by. So therefore, if a, not being 0, but being any other whole number, divides by m, and a also divides by n, okay, then we can say that a will divide by the sum of m plus n, okay? So, for example, if we're saying a is some number and it divides by a whole number m, and then we say that same number a divides by a whole number n, then this theorem says then that same number a will also divide by the sum of the numbers m plus n. Okay? The other thing this theorem states is it also says if a divides by m and it also divides by n, then a will also be divisible by the difference of those two numbers. Okay? And last but not least, if a divides by m, then it will be divisible by a multiple of m. That's what this means. A is divisible by km, meaning multiple. So basically, if a is any number and it divides by m, and it also divides by n, it will be divisible by their sum. If a is any number and it divides by m, and it also divides by n, it will be divisible by their difference. And if a divides by m, it will be divisible by any multiple of m. That is what the theorem tells you. So it's good to remember that because you will see later how we apply that to some of our divisibility rules. That's why it's important for you to note this theorem of 5.3, okay? Because the theorem states that these relationships exist. So let's look at an example of that, okay? If we let a be 3, okay? And remember, it's not divides by. My mistake. I keep saying divides by. It means divides. In other words, a divides the number it's coming into. In other words, goes into. It might be a better way of saying that. My mistake. So let me repeat that. The official term for that line is divides, but what it means is goes into evenly. So if a goes into m evenly and a goes into n evenly, then a will go into the sum of them evenly. And if a goes into m and a goes into n evenly, meaning it divides with a 0 remainder, then a will also divide into the difference of them evenly with a 0 remainder. And the same thing is true. If a goes into m evenly, then a will also divide evenly into any multiple of m. So let's think of it that way, because I think that's less confusing, and my apologies for initially not making it that clear. So here's an example. We're going to say that a is 3, okay? And we're going to say it's going to divide 27. In other words, goes into m, 27. And then we're going to say that n is 9. So it's going to go into 9, okay? And we're going to say that k, that's the multiple we're going to use, is going to be 2. then according to this theorem, A will divide evenly into 27, which it does, because it goes in by 9 with a remainder of 0. And therefore, it will go into 9 evenly, which it does. It goes into 9 3 times with a remainder of 0. And it should, according to this theorem, then go into the sum of 27 plus 9 evenly. Well, 27 plus 9 is 36. And sure enough, 3 goes into 36 evenly, goes in 12 times with a remainder of 0. Okay? Let's try another one. All right, let's try the second portion of that theorem. The second portion of the theorem says that if A goes into 27 evenly, which it does, giving us 9 with a remainder of 0, and A, which is 3 for this scenario, goes into 9 evenly, because 9 represents n in this scenario, and it does evenly, it goes in 3 times with a remainder of 0, then A should go into their difference evenly. Now the difference between 27 and 9 is 18, and A, being 3, does divide into 18 evenly, goes in 6 times with a remainder of 0. Okay? Now, last but not least, Theorem 5.3 says that if A goes into 27 evenly, and then it should go into any multiple of 27 evenly, right? So let's see. We know that A goes into 27, divides into 27 evenly. It goes in 9 times with a remainder of 0. So therefore, if we take a multiple of 27, in this case we said that the multiple would be times 2. So we're going to say 27 times 2, which is 54. A should, according to this theorem, divide into 54 evenly with a remainder of 0. If you put that into your calculator, it sure does. It goes in 16 times with a remainder of 0. So the theorem holds true. And we could pick different numbers and the case would still be the same. Okay? Alright, so now, because that theorem exists, because those relationships exist and hold true, we can then have some of the following theorems that fall into our continuing tests of divisibility. So we're going to look at now the test for divisibilities for 4 and 8. Okay? Now, the divisibility test for 4 says that a number will be divisible by 4 if the last 2 digits, and this is important, 2 digits are divisible by 4. That means no matter how long this number is, if those last 2 digits create a number, a 2-digit number, that is divisible by 4, then the entirety of that number will be divisible by 4. That's what it's saying, okay? Now, it also says, and this is a typo, this should be 8 right here, so we're going to correct that. That should be 8. It says a number is divisible by 8 only if the last 3 digits are divisible by 8. Okay? So for 4, it's got to be the last 2. For 8, it's got to be the last 3. So no matter how large the number is, if the last 3 digits create a number that is divisible by 8 evenly, meaning 8 goes into it with a remainder of 0, then that entire number will be divisible by 8. And if a number, the last 2 digits create a 2-digit number that 4 can divide into evenly with a remainder of 0, then that entire number will be divisible by 4. Okay, so let's look at that example. If we look here, we're testing to see if 4 divides into 1,432. The divisibility test says to look at the last 2 digits. The last 2 digits are 3 and 2, creating the number 32. And we know that 4 does go into 32. You can see it here because it's part of our times tables, right? 4 does go into 32 8 times with a remainder of 0. So therefore, we should expect that 4 will go into 1,432 a certain number of times evenly, and it does. It goes in 358 times. Okay? So that's how it's holding up the divisibility by 4 test, which is included in Theorem 5.4. Then, if we check to see the divisibility by 8, okay, here's the number they gave us. This number, we're going to check the last 3 digits. According to the theorem, that's what we have to look at. The last 3 digits create the number 432. So we go over here and we check. 8 goes into 432, and you can put that into your calculator. And it does go into 432 54 times evenly with a remainder of 0. So because this is true, we know that 8 will go into this whole number, 98,765,432. It will also divide into it evenly, and if you were to put that into your calculator, you would find out that that is indeed the case. 8 goes into 98,765,432, 12,345,679 times evenly. Okay? So it does go into it evenly. All right, so those are your tests for 4 and 8, and that is Theorem 5.4. Let's look at Theorem 5.5, which discusses the divisibility of 3 and 9. Okay, so we're going to look at the divisibility tests for 3 and 9. The divisibility tests for 3 and 9 state the following. Okay, it states that if a number is divisible by 3, it will be so only if the sum of all of its digits is divisible by 3. So that means whatever the size of that number, you have to take all of the individual digits, add them together, and then check to see if that sum 3 can divide into it evenly with a remainder of 0. If that is the case, then that entire number will also be divisible by 3. Okay? And then it states that a number will be divisible by 9 only if the sum of all of its digits is divisible by 9. Okay? So let's look at an example. We want to see if 3 divides evenly into 12,345. To do that, we check the sum. We take each of those digits, add them together. It's 1, 2, 3, 4, 5. We add them together. The sum is 15. 3, we know from knowing our fact tables, divides into 15 evenly 5 times. So because 3 divides into the sum evenly, we can say that it will divide into the entire number evenly, and it sure does. It divides in 4,115 times. Okay? Now let's look at 9. We want to know if 9 will divide into 6,543. We check that by taking the sum of all the digits. So here it is. This is 6543. We're going to add them together. The sum of those digits is 18. From knowing our fact tables, we know that 9 does divide into 18 evenly. It goes in 2 times. So because it fulfills the theorem, we know that 9 will go into 6,543 evenly with a remainder of 0. And if you put that into a calculator, it does. It goes in 727 times. Okay? All right. Let's move on to Theorem 5.6, which is the test for divisibility of 11. Now, this test is a bit complicated, but and it's worthwhile if you need to know if it goes in by 11, but it is a little complicated, so follow me carefully through this, okay? A number will be divisible by 11 only if the number 11 divides into the difference between the sum of all the digits, between the sum of the digits whose place values are odd powers of 10, and the sum of the digits whose place values are the even powers of 10. So the best way to look at this, and I have it worked out right here for you, but I'm going to do it again with you step by step because this is a bit complicated. So let's say that we are checking to see if 11 is going to divide into the number 5,346. Okay? Now, this is ones, so that's an odd power of 10. This is tens, so this is odd, this is even. This is hundreds, okay? This is thousands. So this again would be odd, and this would be even. Okay? So, that being because this here is 10 to the power of 3, and this is 10 to the power of 1. This here would be 10 to the power of 2, and this is 10 to the power of 4. That's how they're deciding odds and evens. Okay? So that being the case, that means that you want to take the sum of the odd powers, so that's 3 and 6, right? So we're going to go 3 plus 6 equals 9. So that's the sum of the odd powers, okay? And then we're going to take the sum of the even powers, that's 5 and 4. So 5 and 4 equals 9. Okay, so that's the sum of the even powers. And then according to the theorem, the difference between them, 9 minus 9 equals 0. So that's the difference between them. Okay, and if 11 divides evenly into the difference, then it will divide evenly into the entirety of the number. Well, 0 divided by 11 is 0 with no remainder. So technically speaking, it does divide evenly. So because that is the case, we can say that 11 will divide evenly into this number. And that, in essence, is what's happening up here, okay? We divided our powers. You can see that I made the odd ones black and the even ones pink, okay? And we checked the odd ones first, and they were the black ones. So here's 3 and 6, right? And they gave us 9. And then we checked the even ones, which were the pink ones, and it was 5 and 4, and they gave us 9. And then here's where we found the difference, and it gave us 0. And we checked, and yes, 11 goes into 0 0 times, so it does go into it. Therefore, we know that 11 will divide into this number evenly, and if you put it into your calculator, it does. It goes into this number 486 times. So I hope that that makes it a little clearer. It's a bit of a tedious test, but when you need to test for it, at least you have a test instead of just checking it randomly. Okay? But that's how the odd and even powers are decided. The even ones are decided because it's the power of 4 and the power of 2, which is an even number. Okay? And the odd ones are decided because these are the powers of 1 and 3, and those are odd numbers. So hopefully that helps to clarify that. Okay? Alright, let's move on to divisibility by 6. This is where that theorem we talked about in the beginning, theorem 5.3, that told us about some relationships that always exist in divisibility, so that if a number can divide into one number evenly, and then it divides into another number evenly, then it's going to divide into the sum of those two numbers evenly, and it will divide into the difference of those two numbers evenly, and it will divide into the multiple of a number evenly. If it divides into the original number evenly, then it will divide into the multiple of that number evenly. That was theorem 5.3 that we talked about at the beginning. So because of those relationships existing is why we can have theorem 5.7 regarding the divisibility of 6. Okay? Because what it says is the following. A number will be divisible by 6 if both the tests for 2 and 3 hold. This makes sense, okay, because those two numbers give you the product for 6. And we just talked about how theorem 5.3 tells you that you can have a multiple of a number, which in essence is a product, right? So, if for 6, you don't have to have a new test. You would have tested already for 2, and you would have tested already for 3. And if it passed both of those tests, then by default, it would also be divisible by 6. Okay? Because 2 and 3 are factors of 6. So here's an example of that. Okay? If we have 6, and we want to know if 6 divides into 36. Okay? If we had already tested 36, we would know that if we'd already tested it by the divisibility test for 3, we would know that 3 divides into 36 evenly. It goes in 12 times. Okay? Because the sum of the digits is equal to 9, which is a test for 3, and 3 divides into 9. So this is this right here is just reminding you of the test for 3. But if we had done that test, we would have discovered that 3 goes into 36, right? And if we had done the test for 2, we would find that 2 also goes into 36 because here's the test for 2. Because the 1's digit is 6, it's an even number, that's the test for 2. So, because 3 goes into 36, and 2 goes into 36, and both of those tests have passed, then we can say 6 will definitely, sorry, I've got these 3 marks here. Then we can say that 6 will definitely go into 36, and we know that it does by 6 times. Okay? So let me erase this here so it's a little less confusing. But basically what we're saying is that because 3 goes into 36, and this is just reminding you of what the test for testing for the divisibility of 3 is. And because 2 goes into 36, and this is just reminding you of what the test for the divisibility by 2 is, then because those two are true, then by theorem 5.7, we can say that this is true, that 6 will also divide into 36 evenly. Hopefully that's clear, okay? And theorem 5.7 exists and is possible because of that theorem 5.3 that we talked about in the beginning that talks about some relationships that always exist when talking about divisibility, okay? Now, what happens if you've tested for all these numbers? Because at this point, we now can test for 2, right? 4, 3, 6, 5, 10, 8, 9, and 11, right? These are all the numbers that we can test for. So, let's say that you have a number and you test for all of these and it does not pass any of those tests. Does that mean that you're looking at a prime number? Not necessarily. You have to also do the prime factor test. You have to test to see if it has prime numbers that are factors, i.e. then they would divide into that composite number that we're talking about evenly, okay? Here's an example. So, that's what this note right here is telling you. It's telling you to be aware that if a number fails all the other divisibility tests before, and that's the important part, so I'm going to highlight that, before stating that that number is a prime number, you have to check to see if it has any factors that are also prime numbers. And remember that this has to be other than 1 in itself, because every number has 1 in itself as a factor, right? So you got to check to see if other prime numbers are also factors of this number that you're checking, if it has already failed all the divisibility tests that we've discussed. So here's an example of what we're talking about, okay? Let's say that we're looking at the number 299. If you had taken 299 and checked it, all the divisibility tests we talked about, it fails them, okay? It is not divisible by any of those numbers. So 299 fails all the divisibility tests that we just finished talking about. But we cannot right away run off and say 299 is a prime number. We have to check to see if it has prime numbers as factors. So when you check the prime numbers, okay, you're not going to check 2 because it already failed that, and that's the first prime number. You're not checking 3 because it already failed that, and that was a prime number. And you're not checking 5, okay? Because those 3 prime numbers are already included in our divisibility tests. So you're going to start checking at 7. Okay, 7 doesn't work, but then you move on to 13, and sure enough, 13 does work. 299 divided by 13 gives you 23 with a remainder of 0. So 13 is a factor of 299. Therefore, 299 has more factors than just 1 in itself. It has 1 itself and 13. That being the case, 13 is not a prime number, it is a composite number. Remember, by the definition of what a prime number is. Now, you could do this, but it'd be a little tedious, because what if it hadn't been 13? Then you would have had to check 17, and then from there, if it hadn't been that, you'd have checked the next prime number, which is 19. So it could be tedious. So what did they do? They came up with a way to make it easier, okay? Let's do another example first, and then I'm going to give you the shortcut for figuring it out. So let's look at the number 401. Okay, let's say that we wanted to check to see if 401 is prime. We start by checking all the divisibility tests that we've talked about, and it's not divisible by any of them. It fails all of those tests. So we've already checked 2, 3, and 5 as prime numbers. So now we're going to check other prime numbers. And we check 7 and 13 and 17 and still nothing. And you're going like, when can I stop? Well, here's how you know. The square root of 401, if you put that into your calculator, is approximately 20. It's like 19 point blah, 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 blah. So that tells you that you don't have to check any further than the prime number 19. And if up to the prime number 19, none of those prime factors check out, then you can confidently declare that 401 is prime. Okay? That shortcut, this is what we call it. It's called the prime factor test. And it is a prime number. What you do is less than or equal to the square root of the number you're talking about. Okay? Therefore, you take whatever number you're talking about. In this case, let's say that we wanted to take, I'm trying to think of a number that would be rare. Let me see. Well, let's look at the example we had. If we want to check to see if the 401 is a prime number, then we would take the square root of 401, and we would not have to check beyond the prime number closest to it. The square root of 401 is approximately, I think it's like, actually, you know what? Let me just check that for you instead of guessing, right? Because it makes no sense to guess. All right, so I'm going to get my trusty calculator here. Alright, so we're going to take the square root of, let me see, 401, and the square root of it is 20.0249843. So you can see that it's approximately 20. So the nearest, that's why this says less than or equal to. The nearest prime number that is less than or equal to 20 is 19. It is less than 20, and that is the closest prime number. So that means I do not have to check beyond 19. Once I realize that 401 has failed my divisibility tests, the prime numbers I have to check are 19 and smaller. I've already checked 2, 3, and 5 in my divisibility tests, so that means I would only have to check 7, 13, and 19. And if those don't go into 401 evenly, I can confidently declare that 401 is a prime number. Okay? All right. So with that, we come to the close of section 5.1. I'm going to go ahead and stop my share here. All right. The homework assignment that goes with this is homework number 10. It's already up on your task bar. It is page number 185 to 186. You're going to do number 7 through 14. Okay, that is your homework. It will be due by 1 p.m. on Friday before our live Zoom class. And as always, I will have the video for Friday's assignment and homework already put up as well, so you can access that immediately after our live class. All right, guys, take care and have a wonderful day.